How is information encoded in qubits? Imagine a tiny particle that can hold more than just a simple yes or no answer. That's what makes qubits so fascinating in the world of quantum technology. Unlike classical bits that are either 0 or 1, qubits can be in a mix of both at the same time. This is possible because of a principle called superposition, where a qubit exists as a combination of the two states, each with a certain probability. Think of it like a spinning coin that is both heads and tails until it lands. The state of a qubit is described by a mathematical object called a quantum state vector. This vector has two parts called complex probability amplitudes, which tell us how likely the qubit is to be measured as 0 or 1. These amplitudes are like weights that determine the qubit's behavior when we look at it. The more balanced these amplitudes are, the more the qubit is in a superposition. If one amplitude is bigger, the qubit is more likely to be found in that state when measured. Qubits are physically made from different systems such as atoms, ions, photons, or superconducting circuits. Each of these systems offers at least two distinct quantum states to representing the logical 0 and 1. For example, in a photon, the states could be different polarizations, while in an atom, they could be different energy levels. Visualizing a qubit on a sphere called the Bloch sphere helps us understand its state. The North Pole might representing 0, the South Pole 1, and any point in between is a superposition. Encoding information in qubits involves preparing them in specific superposition states and then manipulating these states with quantum gates. These gates are like the logic gates in classical computers but work with quantum effects. They can rotate, entangle, or change the amplitudes of qubits, allowing complex operations. Entanglement is a special link between qubits where the state of one instantly influences the state of another, no matter how far apart they are. This connection boosts the power of quantum encoding. There are different ways to encode information in qubits. Basis encoding is the simplest, where classical 0 and 1 directly map to the quantum states 0 and 1. Amplitude encoding uses the amplitudes of multiple qubits to store large amounts of data in a superposition. Angle encoding involves rotating qubits on the Bloch sphere to representing data. Continuous variable encoding uses systems like quantum harmonic oscillators or photon states, which can encode information in an infinite number of states, improving error correction. To keep the information safe from errors, quantum error correction codes are used. These codes spread the information across many physical qubits, making it possible to detect and fix errors caused by environmental noise or decoherence. For example, surface codes arrange qubits in a lattice with entanglement links, creating a robust network that can correct mistakes and maintain data integrity. In real-world quantum computers and communication systems, these encoding methods are essential. They allow us to store, process, and transmit quantum information reliably. This is what makes quantum technology so promising for future computing, secure communication, and advanced algorithms. In essence, information in qubits is stored through their ability to be in multiple states at once and their entangled connections, using various encoding schemes to optimize performance and error resilience. This is the foundation of how quantum systems handle information in the exciting field of quantum technology.